I don't think Flatzoid. I don't think he realizes that when he admitted that the molecules will bounce around freely in all directions and only exert a force on the scales when they hit them in all directions. I don't think he realizes what he's admitted to there.
Gene's answer is not correct. It constitutes a great example of what happens when the laws of thermodynamics are violated. In the end, Genes tried to argue that gravity was responsible for the gradient in temperature observed in the Earth's atmosphere. However, Boltzmann has shown us that this cannot be the case. However, Boltzmann has shown us that this cannot be the case.
That this cannot be the case.
That this cannot be the case.
You understand the atomic model, right? Everything's a particle. Everything's an atom. We've got one gas molecule.
It's
bouncing around freely in all directions inside the vacuum container. And now we stick a set of scales on the bottom. There's only one time when it's going to register a weight for the molecule. We know that you know when that is. We know that you know that we know that you don't want to say so.
When it hits the scale?
Correct. Because you need a force, right?
Okay.
So until it hits the scales, it can't register any measurement on it because it's never it's bouncing near it, but it never hits the scales. And then when it does hit the scales, bang, you get a measurement, and then it's tiny, but it does hit the scales eventually, right? And you'll get a measured weight to that thing, to that molecule.
Yeah.
Right.
Yeah.
Now we're going to put the molecule on the ceiling again, upside down, on the other surface, opposite. When's it going to measure weight? When's it going to measure weight this time?
When it hits the scales again.
Correct. So now we've got the scales on the deck, and we've got the scales upside down. You're saying that atmospheric pressure has got weight, but you've just measured it. You've just demonstrated how it can be measured in both directions evenly.
Because it has weight?
No, because it's bouncing freely in all directions, and the only time that a set of scales measures weight is when there's an impact. There's got to be a force. But if you put the scales on the floor or on the ceiling, let's put it on like the four sides. When is the set of scales going to measure weight when it's on all four sides?
So can you use simpler words?
Not really. This is as simple as it gets.
So can you explain what you're saying?
You've just got it right twice. You said when the scales receive the collision, it'll measure a weight, and it was on the floor. You were happy to tell me then. Now we've put it upside down, and you've agreed that it's when the scales, when the molecule collides with the scale again. Now we're going to go for the four sides all at once. Any of the four sides, doesn't matter which, but we're going to do it 4 times. When will the scales measure the weight of the molecule? Come on, you've just got it right twice.
When it hits the scales again?
Woohoo! So now we've got direction on all six sides, left, right, up, down, forwards, and backwards. And you're going to still tell me that a set of scales will measure weight because when you put it on the deck, it measures weight. But we've just been through how when you put it upside down on the ceiling and on all 4 sides, it'll still measure weight, but it's not in the downwards direction, is it? It's in all directions. What does this do to your definition for...
When a gas molecule bounces around within a container, and at the point where it hits the scale, the scale would measure weight.
Yeah, and if the scale's on any of the surfaces of the cube, it's going to measure weight every time the particle or the gas molecule bounces off it.
Oh,
only when it bounces off it.
Yeah, you're correct.
Yeah, so scales are not measuring weight, are they? Because they're measuring weight in all directions, not just down.
But this is theoretical, of course.
No, this is practically okay. So if you don't think it's practical, right? What would happen to that particle if I took the lid off and now it was no longer a vacuum? What would happen to the particle?
It would escape, wouldn't it?
Yeah, obviously. Air would rush in. That particle would leave immediately. You wouldn't know where that particle's gone anymore because it's gone. You're demonstrating that you understand that gas will escape, the molecule will escape, and the pressure from atmosphere will press into that container, the vacuum. You've just also demonstrated how it's not directional because the weight scales measure in all directions, but you're going to tell me that the sky is a vacuum and the pressure that's down at ground level won't press into that vacuum, even though you just demonstrated it right now with us that it will, as the penny dropped.
So pressure and weight.
I'm not feeling that you've understood, or if you have understood, you want to change topics. You've just demonstrated how the set of scales will measure weight in all directions, and you've just demonstrated if you took the lid off, that particle would immediately escape, and all air that was in there will press immediately into that container. Yet, you're going to insist that the sky's a vacuum, and that doesn't happen with the Earth.
Yeah, it's theoretical what you say, because over a large surface area, the scales wouldn't pick up any weight. Because there's billions of gas molecules going to be pressing against, going to be like, not like over a large surface area on over that scale, it's going to not really pick up any weight at all, just like how you could hold it underwater and it wouldn't pick up any weight underwater either.
Just give me one concise sentence for what you just said.
The scale wouldn't pick up, like if you were to hold a scale underneath the water, it wouldn't register weight.
Yeah, why would that be?
Buoyancy, right?
Hang on. Before we move away from this last point, I want to conclude the last point, because you've just admitted that when you take the lid off, the molecule will escape. The other thing that will happen is all the air that's outside will press into it immediately, right? But you've just explained to me how the weight will be measured in all directions, not just down. And you've also demonstrated how the pressure will press into that vacuum the minute the lid is removed, and that molecule will disappear into space or into the immediate. It'll just vanish from the box. Yeah,
but
I want you to acknowledge. I want you to acknowledge that's what you've just said.
Yes, but it's theoretical.
So, nah, then.
No, it's in theory. It is possible.
So how would it be different in real? How would it be different in real world then?
Because we don't really get just one molecule of gas.
But you've just correctly described to me how the atomic model would describe the behavior of one particle in a vacuum chamber, and when you remove the lid, you just correctly described that.
Which is what I said before about it being not what I said before about the let's say.
So then you would agree with me then that the atmospheric pressure is not only in the downwards direction, then it's in all directions.
What I said before, the free expansion of gas itself is not labeled as one of the classical gas laws.
Yeah, I've asked you for the citation for that, and you haven't produced it yet.
That's what I said before.
Yeah, but Fight the Flat Earth says a lot of things that are not right either. And if you can't demonstrate it with citation, Hitchens' razor applies. You've got to support it. I don't think Flatzoid, I don't think he realizes that when he admitted that the molecules will bounce around freely in all directions and only exert a force on the scales when they hit them in all directions. I don't think he realizes what he's admitted to there. Do you know what Brownian motion is? Yes or no?
No. What's that?
Right. Brownian motion is basically where that shark is suspended within its medium and it's floating. It's neither going up nor down. It's sat there and it's not moving in any direction because he's not asking it to. It's just floating in its medium, right? Brownian motion is the behavior of the gas molecules on the outside that are randomly hitting it in all directions in 360 degrees, not from the top to the bottom, in all directions. Now that shark the shark is subject to Brownian motion when it's not being accelerated by the remote control, when it's just sat there. There's loads of demonstrations of this. You can see it everywhere online. There's balloons that are not moving and stuff, but it's subject to Brownian motion. The very fact that Brownian motion exists debunks the notion that there's a downwards acceleration to air, because if there was a downwards acceleration to air, Brownian motion couldn't exist because it wouldn't be random in all directions. It would be directional with respect to gravity in the center of Earth. But Brownian motion doesn't reference the center of Earth in its definition. Brownian motion says clearly it's random in all directions all of the time. But you've never heard of it, so we can't really explain it any further than that. So we'll just have to unless you want to bring it up. Oh, yeah, he's bringing it up now. He's bringing it up on screen. Can you see on screen?
Mm-hmm.
He's going to show how these molecules in this example. I've never seen this video before, so I'm not really... Oh, randomly. The keyword random. Not directional. Not down. Not down. I don't know what this is saying here, so I've never seen it. It's showing how
supported
it's going to be
by a fluid. In this case, that fluid is a gas. You are unable to see the gas particles directly because they are too small but you can see the larger dust particles. The reason that the dust particles move randomly are because of the gas. We know that the gas is there because every time we move our hand through the air, we feel them against our hand.
So not down then. Randomly in all directions, but you can see the... I've never seen this video before. It's the first time I've seen it. But he's saying that you can see the dust particles and they're moving randomly in all directions. You've been into your loft space before in your house and you found a little beam of light coming through a little tiny hole, and you see that the molecules, the gas, the dust molecules are all randomly moving in no particular direction, but they're all moving. You've seen that. You must have seen that in your house, right?
Well, gas molecules moving.
No, the dust particles. That video was making the point that the dust particles are moving freely in all directions. But you can see this yourself. On a sunny day, go into your loft space and find a hole in the roof, a little hole somewhere, and there'll be a beam of light. And you can see the dust particles are catching the light to your eye. And you can see that they're randomly moving in all directions. If there was a downwards direction to gas, to the atmospheric pressure that we're breathing, all of the molecules would have a directionality towards the ground. They can't be moving randomly in all directions, but in real world, they actually do. So now my question is, which one's conceptual? Atmospheric pressure or real world demonstration where you can see yourself that the molecules are moving freely in all directions, immediately debunking the notion that atmospheric pressure is a downwards directionality of gas, and therefore the air that we breathe.
Gene's answer is not correct. It constitutes a great example of what happens when the laws of thermodynamics are violated. You end up with non-intensive temperatures. That is why I have highlighted for you that wherever you see a non-intensive temperature, you know that something is wrong. In the end, Genes tried to argue that gravity was responsible for the gradient in temperature observed in the Earth's atmosphere. However, Boltzmann has shown us that this cannot be the case. You will obtain a gradient in temperature which has absolutely nothing to do with gravity and has everything to do with proximity to the heat source.
You will obtain a gradient in temperature which has absolutely nothing to do with gravity and has everything to do with proximity to the heat source.